And now in this lecture we'll answer two questions. In the first question we'll find out the area of this rectangle ABCD that blocks the circle, and in the second question we'll find out the area of this trapezoid ABCD. So we'll start with the first question. In the drawing we have a circle that is inscribed by rectangle ABCD, or rectangle ABCD blocks this circle. In addition, we know that this is called EF, that is equals to 12 units in its length. This is line segment FG, that is equals to 10 units. Again, our mission is to find out the area of this rectangle ABCD. So first of all, we know that all the angles inside the rectangle are right angles. So this angle is a right angle. And we also know that the area of any rectangle equals to the length of the rectangle times the width. We will define the length of this rectangle ABCD as AB. And we will define the width of this rectangle ABCD as dA. We will also define the radius of this circle as R. Point O is the center of this circle. Point M is the point of the circle itself. Therefore, OM is the radius of this circle that is equal to R. The radius OM that is equal to R, the radius OM is drawn to point M, that is the point of tendency of tangent DC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If this is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and N together by a straight line. ON is of course the radius of this circle that equals to R. The radius ON that is equal to R, the radius ON is drawn to point N, that is the point of tendency of tangent AB with this circle. And whenever your radius is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. If AB is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. Point E is the point of tendency of tangent DA with this circle. We will join points O and E together by a straight line. OE is of course the radius of this circle that is equal to R. The radius OE that is equal to R, the radius OE is drawn to point E, that is the point of tendency of tangent DA with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent DA will be perpendicular to the radius EO. If DA is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. By doing this construction, you can do the small quadrilateral DMOE. Inside the small quadrilateral DMOE, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4-facing angle. In total, they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4-facing angle must be equal to 90 degrees in its size. Likewise, in the lower quadrilateral EONA, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees, so 270 degrees plus the size of this fourth missing angle. In total, they must be equal to 360 degrees, according to the same rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So the size of the big angle MON is equal to 90 degrees plus 90 degrees, that is 180 degrees. So I write it down. The big angle MON is equal to 180 degrees in its size. And we know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. Therefore, line 7 MON is a straight line. If line 7 MON is a straight line, then MN is also a straight line. MN is a straight line that touches the circle at 2 points, point M and point N. Therefore, MN is a chord MN is a chord that passes through point O, that is the center of the circle. And we know that any chord that passes through the center of the circle, it is defined as a diameter. Therefore, MN is the diameter of this circle. MN is the diameter of the circle. So it is known, MN is the diameter of the circle. So anyway, MN is the diameter, it is absolutely a straight line. So therefore, shape DMNA is a quadrilateral because it consists of 4 sides. 1, 2, 3, 4. So shape DMNA is a quadrilateral with 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be less a rectangle if not a square. So we relate to the big quadrilateral DMNA is a rectangle because it has 4 right angles. So I did not. This is the big quadrilateral DMNA, that is a rectangle according to rule 5. The quadrilateral DMNA is a rectangle. But we also know that the opposite sides of rectangle are equal to each other. So in the big rectangle DMNA, side DA must be equal to the opposite side MN. So in rectangle DMNA, side DA must be equal to the opposite side MN. But we already found out that MN is the diameter of the circle, so we can write here that MN is the diameter of the circle. And according to our definition, DA is the width of rectangle ABCD. So I write it down. DA is the width of rectangle ABCD. In the next step, we will extend the radius EO by a straight line until it touches the circle. And we will define the touching point of the extended radius EO with this circle. This point is point L. EO is the radius of this circle. It is absolutely a straight line. And when you extend a straight line by straight line, the result EL must be also a straight line. So EL is a straight line that touches the circle at 2 points E and L. And therefore EL is a chord that passes through point O, that is the center of the circle. And we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore EL is the diameter of this circle. So you can write here that EL is the diameter of this circle. And from this long equation, the width equals to DA equals to MN equals to the diameter equals to EL. We will derive that EL is the width of rectangle ABCD. Repeat again. On this long equation, we will derive that EL is the width of rectangle ABCD. In the next step, we will join points L and F together by a straight line. By joining points L and F, we create a peripheral angle EFL. This is peripheral angle EFL that subtends on EL, that is the diameter of the circle. And according to rule 7, any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in size. Therefore, peripheral angle EFL is equal to 90 degrees in size according to rule 7. So, repeat quickly on rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. So in the drawing, we have a circle. AB is the diameter of the circle. This is peripheral angle ACB that subtends on AB, that is the diameter of this circle, and therefore peripheral angle ACB is equal to 90 degrees in its size. We have already implemented rule 7 in our drawing. Why? Because in our drawing, this is peripheral angle EFL that subtends on EL, that is the diameter of this circle, and therefore peripheral angle EFL must be equal to 90 degrees in its size. So in the right angle EFL, we define this angle is alpha, so this angle equals to alpha, this angle equals to 90 degrees, therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. In the next step, we will extend the diameter EL by straight line until it touches side CB of this triangle ABCD. And we will define the touching point of the extended diameter EL with side CB, this point as point T. ET is definitely a straight line because we extended the radius EL, that is a straight line by straight line. When we extend the straight line by straight line, the result ET must be also a straight line. So by doing this construction, we can do the big quadrangle ETBA. Inside the big quadrangle ETBA, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees. According to the rule that states that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So inside the big quadrangle ETBL, we have 4 rectangles, and according to rule 5, any quadrangle that has 4 rectangles must be this rectangle if not a square. So we relate to the big quadrangle ETBL, ETBA is a rectangle because it has 4 rectangles. So already know. Quadrangle ETBA is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle ETBA, side ET must be equal to the opposite side AB. So I did not. The rectangle ETBA side ET must be equal to the opposite side AB. But AB is the diameter, AB is the length of this rectangle ABCD, so we can write here that AB is the length of rectangle ABCD, and from this equation ET equals to AB equals to the length, we will derive that ET is also the length of rectangle ABCD. ET is the length of rectangle ABCD. So in conclusion, we found out that EL is the width of rectangle ABCD, and ET is the length of rectangle ABCD. And again, ET is the length of rectangle ABCD, and EL is the width. In the next step, we will focus on the big right triangle ETG. The big right triangle ETG, this angle equals to alpha, this angle equals to 90 degrees, therefore this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. It is very easy to see that the big right triangle ETG is similar to the small right triangle ELF. Anyway, I prove that those two right triangles are similar to each other. So why those two right triangles are similar to each other? First of all, this is angle E, that is also defined as angle alpha. Angle E is a common angle that belongs to both triangles. Angle E belongs to the small right triangle ELF, and angle E also belongs to the big right triangle ETG. So we can write down that angle E equals to itself is a common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees once alpha, therefore they are equal to each other. So I found out that all the triangles of the big right triangle ETG are correspondingly equal to all the triangles of this small right triangle ELF, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. We actually found out that the big right triangle ETG is similar, this is the sign of similar, to the right small triangle, triangle ELF, according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side ET of the big right triangle ETG over side EF of the small right triangle ELF is equal to side EG of the big right triangle ETG over side EL of the small right triangle ELF. So repeat again. From the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side ET of the big right triangle ETG over side EF of the small right triangle ELF is equal to side EG of the big right triangle ETG over side EL of the small right triangle ELF. ET is the missing side, so we leave it as it is. Over EF. EF equals to 12 units in its length. And it is equal to EG. EG in total equals to 12 plus 10, that is 22. Over EL. EL is the missing side, so we leave it as it is. So in total, we actually found out that ET over 12 equals to 22 over EL. Here we will cross multiply this equation, and we will get that ET times EL is equal to 22 times 12. So ET times EL is equal to 22 times 12, that is 264. So I copy the equation again. I actually found out that ET times EL is equal to 264. But we have already found out that ET is the length of rectangle ABCD, and EL is the width. So we substitute ET in this equation by the length of rectangle ABCD, and we substitute EL by the width of rectangle ABCD. So in total we get that the length of the rectangle ABCD times the width of the rectangle ABCD is equal to 264. The length times the width of rectangle ABCD is equal to the area of rectangle ABCD. So if you found out that the area of rectangle ABCD, that is the area that we are looking for in this question, is equal to 264 square units. And that is the answer to the first question. Repeat again, if you found out that the area of this rectangle ABCD is equal to 264 square units. So we finish with the first question. In the next step, I will present you the second question, and we will solve the second question of this lecture. In the second question, our task is to find out the area of this trapezoid ABCD. So in the drawing we have trapezoid ABCD. We know that side AB equals to line segment AP. We also know that line segment PD equals to side DC. BQ equals to 4 units in its length. Line segment QC equals to 9 units in its length. Those two angles are right angles, and this is angle PQC, that is also a right angle. Again, our task is to find out the area of this trapezoid ABCD. So first of all, we know that AB equals to AP, so if we define the length of side AB as A, then the length of this side AP must be also equal to A, because they are equal to each other according to what is given as the question. Likewise, line segment PD equals to line segment DC. So if we define the length of line segment PD as B, then the length of side DC must be also equal to B, because they are equal to each other according to what is given as the question. In the next step, we will join points B and P together by straight line. And we join points P and C together by straight line. By joining points B and P, we created the right small triangle PAB. In the right small triangle PAB, those two sides are equal to each other, and we have the rule that in front of equal sides in the triangle there are equal angles. So those two angles that are located in front of those two equal sides must be equal to each other in their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha, because they are equal to each other according to the rule that I mentioned. We also know that the sum of the angles in any triangle is equal to 180 degrees. It is true in any triangle, and especially it is true in this right small triangle ABP. So which angles we have in the small right triangle ABP? We have this angle that is a right angle plus those two angles alpha and alpha. So 90 degrees plus 2 alpha must be equal to 180 degrees according to the rule that said that the sum of the angles in any triangle is equal to 180 degrees. Here we will subtract 90 degrees from this equation, and we get that 2 alpha equals to 180 degrees minus 90 degrees, it is 90 degrees. Here we will divide this equation by 2, and we get that alpha equals to 90 degrees over 2, that is 45 degrees. So if we found out that this is angle alpha that is equal to 45 degrees in its size, this is also angle alpha that is equal to 45 degrees in its size. So actually we can conclude from this specific example that any right angle that is also an isosceles triangle will have always the same three angles. One angle is a right angle and the other two angles, each angle is equal to 45 degrees in its size. So in the right and isosceles triangle PDC, those two angles must be equal to 45 degrees in their sizes, each of them. Why? Because it is a right angle, because this angle is a right angle, and it is also an isosceles triangle because side PD equals to side DC. Therefore, those two angles, each of them is equal to 45 degrees in its size. We don't have to repeat on the same proof that those two angles will be equal to 45 degrees, because the proof is exactly the same proof for this right and isosceles triangle ABP. So those two angles must be equal to 45 degrees each of them. AD is one side of trapezoid ABCD, therefore it is absolutely a straight line. So if we focus on the right side of the straight line AD at point P, here the sum of the angles must be equal to 180 degrees, according to the rule that says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the right side of the straight line AD at point P? We have this angle that is 45 degrees, plus this angle that is also 45 degrees, so in total the sum of those two angles is 90 degrees. So 90 degrees plus the size of this third missing angle, in total they must be equal to 180 degrees according to rule 3. Therefore this third missing angle must be equal to 90 degrees in its size. Why? Because 90 degrees plus 45 degrees plus 45 degrees is equal to, in total, to 180 degrees. That is the sum of the angles of the right side of the straight line AD at point P, exactly according to rule 3. So if we define the small angle BPQ, this angle is alpha, then this missing angle QPC, must be equal to 90 degrees minus alpha. Why? Because alpha plus 90 degrees minus alpha is 90 degrees. That is the size of the big angle BPC. Therefore, this missing angle must be equal to 90 degrees minus alpha. So, in the right angle QPC, this angle equals to 90 degrees, this angle equals to 90 degrees minus alpha. Therefore, this third missing angle must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. BC is one side of trapezoid ABCD, therefore it is absolutely a straight line. So if we focus on the left side of the straight line BC at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the left side of BC at point Q? We have this angle that is a right angle according to what is given in the question, plus this missing angle. In total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. So in the right small triangle PQB, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. In the next step, we'll prove that the green right triangle PBQ is similar to the big right triangle PQC. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. In addition, those two angles are both right angles, therefore they are equal to each other. And finally, those two angles are both equal to alpha, therefore they are equal to each other. So I shall prove that all the figures of the big right triangle PQC are correspondingly equal to all the figures of the right green triangle PBQ. And therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. We actually found out that the big right triangle PQC is similar, this is the sign of similar, to the small right green triangle PBQ. According to angle similarity rule. It is very easy to see that side PQ is a common side that belongs to both triangles. Side PQ belongs to the big to the green triangle PBQ, and side PQ also belongs to the big triangle PQC. So PQ is a common side that belongs to both triangles. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side PQ of the big right triangle PQC over side BQ of the small green triangle PBQ is equal to side QC of the big right triangle PQC over side PQ of the small green triangle PBQ. So repeat again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side PQ of the big right triangle PQC over side BQ of the small right triangle PBQ is equal to side QC of the big right triangle PQC over side PQ of the small right green triangle PBQ. PQ is the missing side, so leave it as it is. Over BQ, BQ is 4. And it is equal to QC. QC is equal to 9 units in its length, according to what is given as the question, over PQ. PQ is the missing side, so we leave it as it is. So in total, we actually found out that PQ over 4 equals to 9 over PQ. Here, we will cross multiply this equation, and we will get that PQ times PQ is PQ squared, and it is equals to 9 times 4, that is 36. So PQ squared equals to 36. Here we take a root out of this equation, and finally we get that PQ is equal to the square root of 36, that is 6. So the missing side PQ is equal to 6 units in its length. This is the missing side PQ that is equal to 6 units in its length. In the next step, we will prove that the big right triangle PBC will implement the Pythagoras theorem on the big right triangle PBC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the abbreviation for Pythagoras theorem. The hypotenuse the big right triangle PBC is BC, therefore the square of the hypotenuse is BC square, and BC square must be equal to BP square plus PC square. So if we found out that in the big right triangle PBC, according to the Pythagoras theorem, BC square, that is the square of the hypotenuse, equals to BP square plus PC square. What is the length of the hypotenuse BC? BC in total equals to 4 plus 9, that is 13. Therefore BC square is 13 square, that is 169. So BC square is 169, and it is equal to BP square. What is the value of BP square? We will implement the Pythagoras theorem on the right, the small triangle APB. According to the Pythagoras theorem, in this right small triangle APB, a square plus a square equals to pb square. So pb square equals to a square plus a square, that is 2a square. So bp square equals to 2a square plus pc square. What is the value of PC square? In order to find out the value of PC square, we will implement the Pythagoras theorem on the right triangle PDC. According to the Pythagoras theorem, on the right triangle PDC, B square plus B square equals to PC square. So PC square equals in total to B square plus B square, that is 2B square. So PC square is equal to 2B square. So in total, if we found out that 169 equals to 2B square plus 2A square. So 169 equals to, here we take 2 as a common factor from those two expressions, so inside the brackets we left with a square plus b square. So in total, if we found out that 169 equals to 2 times a square plus b square. Here we divide this equation by 2, and finally we get that a square plus b square is equal to 169 over 2. And again, if we found out that a square plus b square equals to 169 over 2. Our task is to find out the area of this trapezoid ABCD. So what is the area of trapezoid ABCD? Actually, the area of trapezoid ABCD must be equal to the sum of the areas of the three components that trapezoid ABCD consists of. Trapezoid ABCD consists of the right small triangle ABP, so it is the first component, so it is the area of the small right triangle ABP, that is the area of the first component. Trapezoid ABCD consists the second component. The second component is the right big triangle PBC. So plus the area of the second component, that is the area of the big right triangle PBC. And trapezoid ABCD consists of also the third component, that is the right triangle PDC. So it will be also the area of the first component, that is the area of the right triangle PDC. So if we found out that the area of trapezoid ABCD is equal to the sum of the areas of the three components that trapezoid ABCD consists of. That is to say, it is the area of the small right triangle APB plus the area of the big right triangle PBC plus the area of the right triangle PDC. So we find out the area of each component separately, and then we will add the three areas together, and this will be the area of trapezoid ABCD. That is the area that we are looking for in this question. So what is the area of the first component, that is the area of this triangle ABP? The area of any triangle equals to the base of the triangle times the height over 2. The base is AB, that is A, the height AP is also A, divided by 2. So it is A times A over 2, that is actually A squared over 2. So she found out that the area of this right triangle ABP is equal to A squared over 2. Plus the area of the big right triangle PBC. The area of the big right triangle PBC, it is equal to the base BC times the height PQ over 2. Why the height is PQ? Because of the fact that PQ creates 90 degrees with the base BC. Those figures are right angles. So in total, we found out that the area of the big right triangle PBC is equal to the base BC times the height PQ over 2, plus the area of the right triangle PDC. The area of the right triangle PDC is equal to the base DC times the height DP over 2. The base DC is B, the height DP is B, divided by 2. So it is B times B over 2. That is actually B squared over 2. So in total, we found out that the area of this right triangle PDC is equal to B squared over 2. A squared over 2 plus B squared over 2 is A squared plus B squared over 2. What is the value of BC? BC in total equals to 4 plus 9, that is 13, plus times PQ, that is 6, divided by 2. So there on the big triangle PBC is equal to 13 times 6 over 2. So in total, the area of trapezoid ABCD is equal to A squared plus B squared over 2. But we already found out that A squared plus B squared is equal to 169 over 2. Therefore, we substitute A squared plus B squared in this expression by 169 over 2. And we have to divide it by 2. So that's 169 over 2 times 2. And here we have 13 times 6 over 2 is equal to 6 over 2 is 3, and 3 times 13 is 39. So in total, this expression equals to 39. Therefore, ABCD in total will be equal to 169 over 2 times 2 is 4 plus 39. So here we will multiply 39 by 4 and then we divide it by 4 in order to have a common factor with this number, and we will get that in the numerator we have 169, and 39 times 4 is 156 divided by 4. 169 plus 156 is 325 divided by 4. 325 over 4 is 81.25 square units. So we have found out that the area of trapezoid ABCD, that is the area that we are looking for in this question. Is equal to either 325 over 4 square units, so in terms of numbers, the area of trapezoid ABCD is equal to 81.25 square units. And that is the answer to the second question of this lecture. Repeat again, we found out that the area of this trapezoid ABCD is equal to either 325 over 4 square units, so in terms of numbers, the area of this trapezoid ABCD is equal to 81.25 square units. So we finish with the second question. In the next step, I will summarize the lecture. We start with the first question, of course. In the first question, our task is to find out the area of this rectangle ABCD. So in the drawing, we have rectangle ABCD, and this circle is inscribed by rectangle ABCD, or rectangle ABCD blocks this circle. In addition, remember that this is called EF, that is equals to 12 units in its length. This is line 7FG, that is equals to 10 units in its length. Again, our mission is to find out the area of this rectangle ABCD. So first of all, we know that all the angles inside any rectangle are right angles. So the side of this missing angle is 90 degrees. We know that the area of any rectangle equals to the length of the rectangle times the width. We define the length of this rectangle ABCD as AB, and we define the width of this rectangle ABCD as DA. Okay? The length is AB and the width is DA. We define the radius of this circle as R. Point O is the center of the circle, point N is the point on the circle itself, therefore ON is the radius of this circle that is equal to R. The radius of N that is equal to R is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NO. If AB is perpendicular to NO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and M together by a straight line. OM is the radius of this circle that is equal to R. The radius of OM is drawn to point M, that is the point of tendency of tangent DC with this circle. And whenever your radius is drawn to the point of tendency, then tangent DC will be perpendicular to the radius MO. If DC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle equals to 90 degrees according to the same rule, rule 1. Point E is the point of tendency of tangent DA with this circle. We join points O and E together by straight line. OE is of course the radius of this circle that is equal to R. The radius of OE is drawn to point E, that is the point of tendency of tangent DA with this circle. And whenever your radius is drawn to the point of tendency, then tangent DA will be perpendicular to the radius EO. If DA is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule, rule 1. By doing this construction, you can deduce the small quadrilateral DMOE. Inside the small quadrilateral DMOE, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees. So 270 degrees plus the size of this 4 facing angle, in total they must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4 facing angle must be equal to 90 degrees in its size. Likewise, in the lower quadrilateral EONA, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees, so 270 degrees plus the size of this 4 facing angle, in total they must be equal to 360 degrees according to the same rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this 4 facing angle must be equal to 90 degrees in its size. So the big angle MON is equal to 90 degrees plus 90 degrees, that is 180 degrees. So the size of the big angle MON is 180 degrees. And you know that any angle that is equal to 180 degrees in its size, it is defined as a straight line. Therefore, line 7 MON is a straight line. If line 7 MON is a straight line, then MN is also a straight line. MN is a straight line that touches the circle at 2 points, point M and point N. Therefore, MN is a chord that passes through point O, that is the center of the circle. And we know that any chord that passes through the center of the circle must be the diameter of the circle. Therefore, MN is the diameter of the circle. MN is the diameter of the circle. So, MN as a diameter, it is absolutely a straight line. Therefore, the big shape DMNA has 4 sides. 1, 2, 3, 4. Therefore, shape DMNA is a quadrangle because it has 4 sides. So in quadrangle DMNA, we have 1, 2, 3, 4 right angles. And according to rule 5, any quadrangle that has 4 right angles must be at a rectangle in front of square. So we relate to the big quadrangle DMNA is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in the big rectangle DMNA, side MN must be equal to the opposite side DA. Okay, MN must be equal to the opposite side DN. So here, in rectangle DMNA, side DA must be equal to the opposite side MN. But DA, according to our definition, is the width of rectangle ABCD. So we can write here that DA is the width of rectangle ABCD. And we just write our formula that MN is the diameter of the circle. So we can write here that MN is the diameter of the circle. Okay, so in the next step, we extended the radius EO, that equals to 1. We extended the radius EO by side line until it touches the circle. We define the touching point of the extended radius EO with the circle. This point is point L. So EO is a radius, it is absolutely a straight line. And when you extend a straight line by straight line, the result EL must be also a straight line. So EL is a straight line. EL is a straight line that touches the circle at 2 points, E and L. Therefore, EL is a chord that passes for point O, that is the center of the circle, and we know that any chord that passes for the center of the circle must be the diameter of the circle. Actually, EL passes for point O because of the fact that we extended the radius EO by side line. So, definitely EL passes for point O because we extended the radius EO from point O until it touches the circle. So EL definitely passes for point O, that is the center of the circle, and we know that any chord that passes for the center of the circle must be the diameter of the circle. Therefore, EL is the diameter of the circle. So we can write here that EL is the diameter of the circle. And from this long equation, the width equals to AD equals to MN equals to the diameter equals to EL. We will derive that EL is also, EL is the width of rectangle ABCD. EL equals to the width of rectangle ABCD. Okay? In the next step, we join points L and F together by straight line. By joining points L and F, we created peripheral angle LFV. Peripheral angle LFV subtends on EL, that is the diameter of the circle, and we know that any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in size. Therefore, peripheral angle LFV is equal to 90 degrees in size according to rule 7. So in the right angle ELF, this angle equals to 90 degrees. We define this angle as alpha. So in the right angle ELF, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third distance angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in the triangle. In the next step, we extended the diameter EL of this circle by side line until it touches side CB of rectangle ABCD. We define the touching point of the extended diameter EL with this side CB. This point is point T. Actually, ET is a straight line because EL is a straight line, and when you extend a straight line by straight line, the result ET must be also a straight line. So ET is a straight line. By doing this construction, we created quadrangle ETBA. Inside quadrangle ETBA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth facing angle. In total, they must be equal to 360 degrees, according to the rule that says that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore, this fourth facing angle must be equal to 90 degrees in size. So, inside the big quadrangle ETBA, we have 4 right angles, and according to rule 5, any quadrangle that has 4 right angles must be at its rectangle if not a square. So we will relate to the big quadrangle ETBA as a rectangle because it has 4 right angles. But in rectangle ETBA, the opposite sides must be equal to each other. That is to say, side ET must be equal to the opposite side AB. So repeat again, in the big rectangle ETBA, in the big rectangle ETBA, side ET must be equal to the opposite side AB. But AB is the length of rectangle ABCD according to our definition. So you can write here that AB is the length, and from this equation ET equals to AB equals to the length, we will derive that ET is also the length of rectangle ABCD. So ET is the length of rectangle ABCD, and we have already found out that EL is the width of rectangle ABCD. Okay, so in the next step, we'll focus on the big right triangle ETG. On the big right triangle ETG, this angle equals to alpha. This angle equals to 90 degrees. Therefore, this perpendicular angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. In the next step, we prove that the big right triangle ETG is similar to the small right triangle ELF. So why those two right triangles are similar to each other? First of all, this is angle E that is also defined as alpha. Angle E is the common angle that belongs to both triangles. Angle E belongs to the small right triangle ELF, and angle E belongs also to the big right triangle ETG. So we can write down that angle E equals to itself is the common angle that belongs to both triangles. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. Finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we can find out that all the three angles of the right big triangle ETG are correspondingly equal to all the three angles of the right small triangle ELF. And therefore those two right angles are similar to each other according to angle similarity rule. So again, we actually found out that the big right triangle ETG is similar, this is the sign of similar, to the right front triangle ELF according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side ET of the big right triangle ETG over side EF of the small right triangle ELF is equal to side EG of the big right triangle ETG over side EL of the small right triangle ELF. So again, from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side ET of the big right triangle ETG over side EF of the small right triangle EFL is equal to side EG of the big right triangle ETG over side EL of the small right triangle ELF. ET is the missing side, so we leave it as it is. EF equals to 12 units in length according to what is given in the question. EG in total equals to 12 plus 10, that is 22, over EL. EL is the missing side, so leave it as it is. So in total, we actually found out that ET over 12 equals to 22 over EL. Here, of course, multiplied this equation and finally found out that ET times EL is equal to 22 times 12. 22 times 12 is 264, so in total, we actually found out that ET times EL is equal to 264. Then again, we found out that ET times EL equals to 264. But we already found out that ET is the length of rectangle ABCD and EL is the width of rectangle ABCD. So we can substitute ET by the length and EL by the width of rectangle ABCD. So in total, we actually found out that the length of rectangle ABCD times the width of rectangle ABCD is equal to 264. The length times the width of rectangle ABCD is the area of rectangle ABCD. So in total, we actually found out that the area of rectangle ABCD, that is the area that we are looking for in this equation, is equal to 264 square units. So repeat again, we actually found out that the area of rectangle ABCD is equal to 264 square units. So we finish with the first question. In the next step, I presented to you the second question, and you solve the second question of this lecture. Our task in the second question is to find out the area of this trapezoid ABCD. So, in the drawing we have trapezoid ABCD, side AB equals to line 7 AP, line 7 PD equals to side DC, BQ equals to 4 units in its length, QC equals to 9 units in its length, This is angle PQC, that is right angle. Those two angles are also right angles. Again, our mission is to find out the area of this trapezoid ABCD. So we know that AB equals to AP, so if we define the length of side AB as A, then the length of side AP must be also equal to A, because they are equal to each other according to what is given as the question. Likewise, PD equals to DC. So if we define the length of side PD as B, then the length of side DC must be also equal to B, because they are equal to each other according to what is given as the question. In the next step, we join points B and P together by straight line, and we join points B and C together by straight line. By joining points B and P, we get the right small triangle, triangle ABP. In the right small triangle ABP, AB equals to AP. And we have the rule that in front of equal sides in the triangle, there are equal angles. So in front of those two equal sides, in triangle ABP, there are those two angles that must be also equal to each other and their sizes, because they are located in front of those two equal sides. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha, because they are equal to each other according to the rule that I mentioned. So in the right triangle ABP, the sum of the angles must be equal to 180 degrees. So which angles we have in the right triangle ABP? We have this angle that is 90 degrees, plus alpha, in total they must be equal to 180 degrees. So 90 degrees plus 2 alpha equals to 180 degrees. We subtract 90 degrees from this equation, and when we found out that 2 alpha equals to 180 degrees minus 90 degrees, it is 90 degrees. So 2 alpha equals to 90 degrees. We divided this equation by 2, and finally found out that alpha equals to 90 degrees over 2, that is 45 degrees. So this is angle alpha that is equal to 45 degrees in size, and this is also angle alpha that is equal to 45 degrees in size. So the small triangle APB is the right and associated triangle. We can conclude from this example that any right and associated triangle has three angles. One angle is the right angle, and the two other angles must be also equal to 45 degrees in their sizes. It is true in any right triangle that is also an associated triangle. So we don't have to repeat on the same proof on the right and associated triangle, triangle PDC. Those two angles must be equal to 45 degrees in their sizes. Triangle PDC is right triangle because this angle is right angle, and it is also an associated triangle because PD equals to DC. So those two angles must be also equal to 45 degrees in their sizes. So we know that AD is one side of trapezoid ABCD, therefore it is absolutely a straight line. So if we focus on the right side of the straight line, AD is point P, here the sum of the angles must be equal to 180 degrees, and according to rule 3, it said that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the right side of AD at point P? We have this angle that is 45 degrees, plus this angle that is 45 degrees, in total is equal to 90 degrees. So 90 degrees plus the size of this fourth missing angle, in total they must be equal to 180 degrees according to rule 3. Therefore this third missing angle must be equal to 90 degrees in its size. This is to say the missing angle BPC must be equal to 90 degrees in its size. Why? Because 90 degrees plus 45 degrees plus 45 degrees, in total it is 180 degrees. It is the sum of the angles on the right side of the straight line AD at point P. Exactly according to rule 3. So this third missing angle BPC must be equal to 90 degrees in its size. In the next step we define the small angle BPQ as alpha. Therefore this missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha, it is equal to 90 degrees, that is the size of the big angle BPC. Therefore this missing angle must be equal to 90 degrees minus alpha. So in the big triangle PQC, this angle equals to 90 degrees minus alpha, this angle equals to 90 degrees, therefore this third missing angle must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. BC is one side of trapezoid ABCD, therefore it is absolutely a straight line. So if we focus on the left side of the straight line BC at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have on the left side of BC at point Q? We have this angle that is a right angle, plus this missing angle, in total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. So in the right great triangle BPQ, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. In the next step, we prove that the big small triangle PBQ is similar to the big right triangle PQC. So, why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to alpha, therefore they are equal to each other. So we shall prove that all the angles of the big right triangle PQC are correspondingly equal to all the angles of the right triangle PBQ. And therefore those two right triangles are similar to each other according to angle similarity rule. So if we do it, we shall find out that the big right triangle PQC is similar, this is the sign of similar, to the right small green triangle PBQ according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides, but before that, PQ is a common side that belongs to both triangles. PQ belongs to the green triangle PQB, and PQ also belongs to the big right triangle PQC. So from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side PQ of the big right triangle PQC over side BQ of the small green triangle PBQ is equal to side QC of the big right triangle PQC over side PQ of the green small triangle PQB. And again, from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side PQ of the big right triangle PQC over side BQ of the small right triangle PBQ is equal to side QC of the big right triangle PQC over side PQ of the small green triangle PBQ. PQ is the missing side, so we limit the cities. BQ is 4, QC is 9, and PQ is the missing side, so we limit the cities. So in total, we shall find out that PQ over 4 equals to 9 over PQ. Here we first multiply this equation and finally found out that PQ times PQ, that is PQ square, is equal to 9 times 4, that is 36. So PQ square equals to 36. We took out all the equation and finally found out that PQ equals to the square root of 36, that is 6. So there is inside PQ equals to 6 units in its name. In the next step, we implemented the Pythagoras theorem on this big right triangle PBC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So here, by PT is the implementation for Pythagoras theorem. The hypotenuse on the big right triangle PBC is BC. Therefore, the square of the hypotenuse is BC square, and BC square equals to BP square plus PC square. Repeat again, in the big right triangle BPC, according to the Pythagoras theorem, BC square, that is the square of the hypotenuse, must be equal to BP square plus PC square. BC, in total, BC is 4 plus 9, that is 13, therefore BC square is 13 square, that is 169. Okay, BC square equals to 169, and it is equal to BP square. What is the value of BP square? In order to find out the value of BP square, we implemented the Pythagoras theorem on the right small triangle ABP. According to the Pythagoras theorem, in the right small triangle APB, a square plus a square equals to BP square. So BP square is a square plus a square, that is 2a square. So BP square equals to 2a square plus PC square. What is the value of PC square? In order to find out the value of PC square, we implemented the Pythagoras theorem on the right triangle PDC. According to the Pythagoras theorem, in this right triangle PDC, b square plus b square equals to pc square. So pc square in total equals to b square plus b square, that is 2b square. So pc square equals to 2b square. So in total we should find out that 169 equals to 2a square plus 2b square. So 169 equals to, here we took 2 as a common factor out of this expression, so inside the brackets we left with a square plus b square. So in total we should find out that 169 equals to 2 times a square plus b square. Here we divided this equation by 2 and finally found out that a square plus b square equals to 169 over 2. Our mission is to find out the area of this trapezoid ABCD. So what is the area of trapezoid ABCD? Actually, the area of trapezoid ABCD must be equal to the sum of the areas of the three components that trapezoid ABCD consists of. Trapezoid ABCD consists of the small right triangle ABP, So it is there on the first component. It is actually there of triangle ABP. Trapezoid ABCD consists of the second component, that is the big triangle, the big right triangle PBC. So it is plus there of the second component, that is there of the big right triangle PBC, plus there of the third component that trapezoid ABCD consists of. The first component that trapezoid ABCD consists of is there the right triangle PDC. So it is plus there of the third component, that is there of the right triangle PDC. So repeat again, actually there of this trapezoid ABCD is equal to the sum of the areas of the three components that it consists of. Trapezoid ABCD consists of the right triangle ABP, so it is there of the right triangle ABP, and it also consists of the big triangle PBC, so it is there of the second component, that is there of the big right triangle PBC, plus there of the third component, that is there of triangle PDC. So the sum of the areas of those three components that trapezoid ABC consists of, in total it is equal to the area of trapezoid ABCD. The area of the right triangle ABP is equal to the base AB times the height, that is AP over 2. So it is A times A, that is over 2. A times A is A squared over 2. So the area of the small right triangle ABP is A squared over 2. Plus the area of the big right triangle PBC. The area of the big right triangle PBC equals to the base BC times the height QP over 2. So the area of the big right triangle PBC is equals to the base BC times the height PQ over 2. Times the area of this right triangle DC. Now the big right triangle PDC is the base DC times the height DP over 2. DC is B, DP is also B, so it is B times B over 2, that is B squared over 2. So in total, the area of this right triangle PDC is equal to B squared over 2. A squared over 2 plus B squared over 2 is A squared plus B squared over 2. BC is 13, PQ is 2 over 2. So the area of the big right triangle PBC is 13 times 6 over 2. 6 over 2 is 3, and 3 times 13 is 39. So in total, the area of the big right triangle PBC is 39 square units. And we have also A squared plus B squared over 2. We have already found out that A squared plus B squared, A squared plus B squared is equal to 169 over 2. Therefore, we substitute A squared plus B squared here by 169 over 2, and you have to divide it by 2, which is multiplied by 2. So, the area of trapezoid ABCD is equal to 169 over 2 times 2 plus 39. 169 over 2 times 2 is 4, so it is 169 over 4 plus 39. Here we multiply 39 by 4, and then we divide it by 4 in order to have a common factor with this number. So in total, the numerator will have 169 plus 4 times 39, that is 156 over 4. So in the numerator we have 169 plus 156 is 325 over 4. 325 over 4 is 81.25 square units. So in total, we should find out the area of this trapezoid ABCD, that is the area that we are looking for. It is equal to either 325 over 4 square units, so in terms of numbers, the area of this trapezoid ABCD is equal to 81.25 square units. Okay, thank you very much.